Some of you may be familiar with or have even seen the classic movie A Star is Born. I think there's been like 3 or 4 versions of this. The latest was Bradley Cooper and Lady Gaga, about the story of the life of an aspiring songmaker, musician, who ultimately became a pop star. Well, tonight we're not going to be talking about terrestrial stars. We're going to be talking about celestial stars. And we're going to be talking about how they're born, their life, how they evolve, and what eventually happens to them. And also, I thought one of the things that I'll be talking about is when you're observing a star, one of the things we'll be seeing is there are certain things about the star by you just visually looking at it. For example, its color. That is going to tell you a lot about the star, about its age, about, in fact, even what's going to happen to it. So that's some of the topics for tonight. Now, let me start also with a quote from Carl Sagan, whom I'm sure all of you know, who back in 1973, and I'll just read it, "All of the rocky and metallic material we stand on, the iron in our blood, the calcium in our teeth, the carbon in our genes were produced billions of years ago in the interior of a red giant star. We are all made of star stuff." And we're going to see, in fact, how this is true. So let's talk about the birth of a star. This is one of the first pictures that James Webb Space Telescope took of a star-forming region in the Carina Nebula, which is a area of gas and dust from which stars are formed. And let me just now play a little video clip of that.
All you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
Okay, so what you saw there is a clouds of gas and dust coming together through gravity, forming this what we call a protoplanetary disk that forms not only the stars, but also planets. So this is where star formation comes from, originates from this cloud of gas and dust. Now let's take a look at inside a star. The core of the star is obviously the hottest place of it. There are several layers of a star, but in the core is where all the action takes place. Nuclear fusion is turning hydrogen into helium, and as well as into heavier elements like carbon, oxygen, and so on. So this is sort of the melting pot of where a lot of the elements are occurring. Now, let's move to the birth of a star, to the life and death of a star. Well, first of all, if you look up at the night sky, what we see is a bunch of twinkling stars, but really, as we're going to see, it really tells the story of the fate of the stars of our sun. And the star's fate, believe it or not, is determined mostly by one thing: the mass at birth. So when a star is born, the mass it has at birth determines its ultimate fate. And we'll see why that's true. In fact, let's separate stars that have a mass less than 8 times the mass of our sun. Let's talk about those stars. We'll call these sort of medium stars, medium mass stars, of which, by the way, our sun is one. So an average mass star, at the end of its life, it goes through a phase where it becomes a giant. We're going to see how this happens in a little bit. Then from the giant phase, it shrinks down into a white dwarf, a hot but small, faint star, if you will. Then after trillions of years, tens of trillions of years, white dwarfs may become black dwarfs. Now, tens of trillions of years haven't happened. The age of our universe isn't even that long. So right now, black dwarfs are theoretically what is going to happen. So these are stars less than 8 times the mass of our sun. Stars that are larger than 8 times the mass of our sun will have a different path. So these larger stars, larger massive stars, will first grow into a supergiant, but then rather going into become a white dwarf, they will explode into a supernova. And what we see as a result is in the sky is a supernova remnant. And we'll see an example of this. That supernova, when it explodes, there's 2 paths that are going to happen. And it depends on the core, the size of the core that's left. If the size of the core that's left, because the gravity has shrunk the mass down to a small size, if it's less than 3 times the mass of the sun, what happens is it becomes a neutron star. A neutron star, as you probably have heard of, what in fact an atom is, right? It's protons, which are positively charged particles, and electrons, which are negatively charged. What happens is the gravity is so much that it brings those two together and they neutralize, so it becomes neutrons. So a neutron star is basically more neutrons than anything else, compressed, incredibly small. In fact, it's been estimated that the size of a sugar cube of a neutron star has as much mass as Mount Everest. That's how stuff has got sort of compacted together so much. So this is for cases where the resulting core is less than 3 times the mass of the sun. If it's greater than 3 times, it turns into a black hole. So this is where black holes often come from. And this happens in less than half a second. So there's 2 paths that a massive star can take after it goes through becoming a supergiant, after it explodes into a supernova. It can become a neutron star, or it can become a black hole. So these are the evolutionary paths of stars, but it all is determined from when they were born, what their mass was at birth. Okay, so let's take a look at some sample stars. Our sun, we sort of know. Aldebaran is in the constellation Taurus, Sirius B, Canis Major. A star called Beta Centauri capital A, small a in Centaurus. This is in the southern hemisphere. The nomenclature is such that that indicates it's a part of a binary star, two stars, capital A, capital A, small b, but also another star, Beta Centauri b. So it's triple stars, but this one is one of two in that system. That's what that nomenclature refers to. And Betelgeuse, which is in Orion, which the name may be familiar to most of you. I picked these stars because, as we'll see, these are examples of stars in different phases of evolution. And we'll see what I mean by that next. So let's go back to stars, average stars, like our sun. Let's use that as an example. Remember, there's two categories, those stars that are average mass stars and those stars that are larger than 8 times larger than our sun. So let's take the category of stars that are less than 8 times the mass of our sun. So this is our sun. Our sun is going to last 10 billion years. We're now halfway through it. So the sun is kind of a middle-age star, but it eventually is going to go into become a giant. What's going to happen is it's going to expand out. It's going to cover the orbit, for example, of Mercury, going to collapse, and then it's going to expand back out, cover the orbit of Earth. So we will be consumed by this envelope from the sun. Our sun then, the result will then become a white dwarf and a black dwarf. Now, an example of a giant that today we can see in the sky is Aldebaran. So when you look at Aldebaran, what you know is that is a giant star that used to be an average mass star. So it's in its second stage of life. Sirius B is a white dwarf. So Sirius B is an example of a star that is now in its third stage of life. And of course, right now, we don't have any examples yet of black dwarfs. That's going to happen way in the future. So this is the evolutionary path of some of the example stars that I talked about earlier. Now let's look at examples of higher mass stars. Well, this one particular star, Beta Centauri, is an example of a mass star. Betelgeuse is an example of a supergiant. So Betelgeuse is a star that is after its original star had aged out, became a supergiant. The Crab Nebula is an example of a remnant of an explosion that took place in the year 1050. So back in 1050, Chinese astronomers saw all of a sudden a bright thing in the sky that wasn't there before. That was the beginning of the supernova, or that was the supernova that took place, and what we see now is the remnant of it. The Crab Pulsar, which is in the Crab Nebula, is an example of a neutron star. And there's many examples of black holes, but one in particular that is a example of something that just happened 3 years ago is, for the first time, astronomers caught the result of a black hole being formed. And what it was not seeing the black hole itself. It was this gamma ray burst that occurred by the name of GRB 22109A. So let me play a little video clip about that, because this was the first time, again, that a gamma ray burst indicative of the formation of a black hole occurred.
Black holes are best understood as the result of a massive star collapsing in on itself near the end of its life. An exploding star, or supernova, is another result of this collapse. It blasts part of the star into space. A black hole has no volume, but it does have mass, which is mostly what is left of a star, and as they keep eating everything around them, black holes get bigger, or in scientific terms, more gigantic. Greater black holes have greater no-return zones, where everything that falls into their realm is destroyed forever. However, the event horizon describes this vanishing point. Today, for the first time, we have observed a supernova explosion birthing a black hole. Gamma-ray burst GRB 221009A was one of the most powerful explosions ever recorded. On October 14, 2022, astronomers used the Gemini South Telescope in Chile to see the amazing effects of this explosion. On October 9, 2022, X-ray and gamma-ray observatories in orbit were the first to notice this record-breaking event. It happened 2.4 billion light-years from Earth and was presumably produced by a supernova explosion, giving birth to a black hole. Astronomers from all over the world are working hard to figure out what happened after a huge explosion in space, which is likely the closest and most powerful gamma-ray burst ever seen. Two different teams used the Gemini South Telescope in Chile to look at the bright glowing leftovers of the explosion.
So that was the gamma-ray burst again. And again, the significance of it, that was the first time that we detected through a gamma-ray burst the creation of a black hole. So let's talk about the characteristics and types of stars that are out there. Well, why is it important to know that? As I said earlier, if we observe the color of a star, we can estimate its temperature because a star's color and temperature, as we'll see, are interrelated. So those of you who were out at Quiet Waters last month, when we had our outdoor observing out there, Andy Lomax was describing some of the stars that are blue, some that are red. And the color that we see then in those stars is indicative of their temperature, as we'll see in a second. So by knowing a star's temperature and brightness, we can predict its fate. And we'll see that in a second. Color is determined by temperature. The hotter the star, the bluer it is. The cooler the star, the redder it is. So by looking at the color of a star, we can kind of get an idea of the range of its temperature. And you'll see why this is important in identifying where in this life cycle a star is. Another characteristic that's important, and we've talked about now a few times, is the mass. Generally, mass is in terms relative to the mass of the sun. So the sun equals 1 of mass. We'll see in a minute some of the other stars have mass of 1.2, 1.5. That's all relative to the mass of the sun. That's typically how astronomers here would talk about mass. And the third characteristic I want to talk about is something called luminosity. Imagine that you're looking down the street. Let's say you're looking down Hillsmere Drive at the street lights. The street light closest to you looks very bright. So it has an apparent brightness of something. The streetlights further down look dimmer, but when you get up close to them, they're going to be the same brightness. So astronomers have a measure, something called luminosity, which is a way of standardizing what the brightness, the inherent brightness of a star is. In fact, astronomers have picked a measure of as if you were at a distance of 10 parsecs, which is 3.2 light years per parsec, 32 light years away. So astronomers have defined a distance to measure the brightness of a star at 10 parsecs to kind of standardize and get away from any difference in distance. So luminosity is the inherent brightness of a star, not what we see from here, but if you were at 10 parsecs, what the luminosity would be. So those three things, temperature, mass, and luminosity, are three characteristics of a star that we'll see in a minute how they all play together. So let's take a look at our sample stars. Our sun, we said, is a medium mass star, and because it's the sun, it has a mass of 1, has a temperature of 5,772 Kelvin, and again, because it's relative to itself, it has luminosity of 1. Aldebaran is larger by 1.2 times and luminosity of 439 times. So Aldebaran is much more inherently luminous, but about the same mass. And I'll just go through the others. Sirius B is about the same mass, but very faint, 0.024 times as far as its inherent brightness. Those are the medium mass stars. High mass stars are what you see here. Now, what I'd like to do is to just focus on temperature and luminosity. These are the two key things that if you knew these characteristics, you could tell where the star is in its life cycle. And let's see how that's true. Well, let's graph at the bottom temperature and luminosity. The sun is, as we said, has a luminosity of 1, since everything's relative to the sun. It has a temperature of 5,500 or so degrees. So that's where the sun is on that chart. If we were to chart where Aldebaran is, it's more luminous, but it's cooler. And remember, Aldebaran is an example of a giant because it had gone through already an evolution from being a medium star to be a giant. Sirius B is our white dwarf, which is the third stage, which is, it's hot, but it's very low luminosity. And this is where the white dwarfs sort of live. So the evolution that the sun is going to go through is it's going to go and become a giant, and then it's going to become a white dwarf. And so Aldebaran and Sirius B are two examples of stars that have already gone through that evolutionary process. Let's take higher mass stars, our Beta Centauri. Betelgeuse is an example of a supergiant, and Beta Centauri will become ultimately a supergiant. So let me just stop there, first of all, and see if any questions so far about this. Joan.
Different, sizes of course. Do they stay, are they in their same place in the universe?
Yes. So Joan's, just for the recording, Joan's question is, as they go through different evolutions, do they still stay the same place in the sky? I think is what you're asking. The answer is yes. They just will grow bigger, yes. But that will take millions of years. So some of these stars, for our lifetime, certainly are going to be the same. But we will, in fact, we're going to see in a minute, some evolution of stars that are maybe going to happen in our lifetime. Okay, so this chart with luminosity and temperature is a very important chart that astronomers use to look at the evolutionary lifespan of stars. And in fact, two astronomers, Hertzsprung and Russell, did this for all the stars. And this is the diagram. If you were to plot on here all of the stars that are visible, you would see, for example, what we already saw, which is the sun here, Aldebaran there, and the giants, Sirius there, and the white dwarfs, Beta Centauri up there, and Betelgeuse there. So this diagram, called the HR diagram, is a fundamental diagram that astronomers often refer to because it shows in one picture the evolution of stars and based upon their luminosity and temperature. What you see along what we call the main sequence, which is this thing in the middle, is where most stars live during their lifetime, before they branch off and become giants, or before they become supergiants, or before they become white dwarfs. So stars live on this one line going through the middle of the chart here called the main sequence. Now let's take a look at just the main sequence. The interesting thing about this would be, for example, if you had this chart in front of you, and by the way, I will include a copy of this chart when I send out the email after my meeting with a link to the recording, so you'll have it handy. So, for example, if you go out at night and you take a look at Vega, which is just a little bit above the sun, you can see where Vega is relative to the sun. Well, Vega is, which I'll point out here with the cursor, is right here. So and here's our sun here. So Vega is higher temperature and greater luminosity. And one of the things we know about stars on this main sequence is that the more massive a star is, the greater it is up this diagram. So by looking at the diagram and by looking at a star that you're seeing up in the sky, you can probably have a pretty good idea where it is relative to other stars as far as how massive it is. Furthermore, the further a star is up on this chart, the shorter its lifetime, because it's larger, it's burning its fuel more quickly, so it's going to have a shorter lifetime. So our sun, as I said, has a lifetime of 10 billion years. Further up at the top of the chart, for example, we're now into the maybe hundreds of millions of years. So again, by looking at where you are on this chart, where a star is on this chart, you can see what its lifetime relative to other stars is going to be. Now, we talked about stars, we talked about our sun and so on. Our sun being sort of a star in a single star system. We just have one star, the sun, right? And we have all the planets going around it. There are many systems that have multiple stars, that have two stars together, binary star. Polaris, the North Star, is a binary star. It looks like it's one star, but it's actually two stars. There are stars that are triplets. That Beta Centauri, for example, is part of a three-star system. So there are many combinations of systems out there that just aren't one star. In fact, a large number are binary stars. Many stars are not constant in their brightness. They vary. In fact, some vary on a very predictable rate. Some vary hourly, called fast pulsars. Some vary on the order of days, some on the order of decades. So, but often at a predictable rate. So we have stars that are not constant luminosity that in fact vary. I think one of the most interesting stars are what I call vampire stars. This is the case where there's a white dwarf. Again, a white dwarf is a star that was a medium star that became a giant, then became a white dwarf. So we have a white dwarf next to a red giant. And what it's doing is it's sucking in material from the red giant to the point where it will accrete being it's, if you will, sucking in this material, hydrogen from the red giant to the point where there will be a thermonuclear explosion. It will all of a sudden brighten, and then it'll become faint. And it will start happening all over again over, let's say, decades. So accreting stars are real. In fact, one that's going to go off any moment, supposed to go off in February, is a star called T Coronii Borealis. It's called a recurrent nova because it's recurring. It's a nova that occurs every so often. This occurs every 80 years. It was predicted to go off last year, literally every day. I have colleagues of mine that are looking at this star, waiting for it to go off. People are going to get text messages. It's going to be, all over the place. And it will go from being very, very faint to as bright as Polaris. And it will probably be in the news when it happens. So be on the lookout for hearing about T Coronii Borealis, because astronomers are looking at this happening literally any moment. Okay, any questions up to that point? Yes?
How long will that remain that way?
Good question. So the question is, how long will it remain? It will brighten very quickly, and then in the matter of days, it'll grow faint. So not a very long time. That's why people are trying to catch it, especially when it starts happening.
Why is it cyclic like that?
I'm sorry?
Why is it cyclic like that? Instead of just being constant?
If the question is, why is it cyclical like that? Let me just go back to this example. The only thing I can say, and I'm not an expert on this, is that just by the nature of it, as a secreting material, it's going to get to a certain point where it's going to cause this thermonuclear explosion, and then it'll just start happening. I can't give you any other example, maybe Mark.
I think that, yeah, it has to do with the accretion. It's just not perfectly clear.
Okay, thank you. All right, so let's talk about star stuff. If you remember Carl Sagan's comment about we're all made of star stuff. So let's talk about going back to this cloud of gas and dust that formed the protoplanetary disk that formed a star. Inside the star, as we saw at the very beginning, there's nuclear fusion that's taking place where hydrogen is being converted to helium, carbon, oxygen, and so on. But then when a supernova occurs, what happens is other heavier elements other than helium and carbon and oxygen are formed, silicates and all kinds of other things. So these heavier elements then become part of this cloud of gas and dust. So now this cloud of gas and dust is not just hydrogen and helium, it's getting more and more heavier elements. These heavier elements then, again, become part of successive generations of stars. So this loop is increasing the amount of heavy elements that become part of stars, but also part of planets, because planets are formed from this protoplanetary disk. So when a planet is formed, it's also being formed with all of these heavier elements of carbon, of oxygen, and so on. Now, the planet, when it's formed, and let's say, for example, on Earth, plants absorb minerals in the soil. Minerals in the soil go back to these heavier elements that were created from the star itself and from things like supernova. We eat the plants. So we become minerals from what would have been part of stars, would have been part of the gas and dust, became part of us. So just to summarize what I've talked about this evening, a star's mass, when it's born, determines its ultimate fate. If it's a medium-sized star, it will end up as a white dwarf. If it's a massive star, you'll end up either as a neutron star or a black hole. So if you know the mass of a star today, you can predict what's going to happen when it dies. Nuclear fusion in the core of a star is turning hydrogen into helium and then into these heavier elements. The color of a star says something about the temperature. So if you see a blue star versus a red star, you'll know that the blue star is hotter than the red star. That HR diagram shows you the evolutionary stages and path of stars. So if you go out at night and are looking at a particular star, you can look on that diagram and give you a pretty good idea where it is on that main sequence, or in fact, maybe it's even a giant or a supergiant star. And that'll tell you something about where it is in its lifetime. And supernovae send these heavier elements into the gas and dust cloud, and they form the protoplanetary disk, which planets are formed, minerals absorbed by plants that we eat, and lo and behold, we are indeed made of star stuff, which is what Carl Sagan said, and the reason why. So that's what I have for this evening. Let me open it up for any questions.
Does the temperature of the star dictate its life, or is it always the same?
Combination of the combination. The question is, does the temperature determine its life? It's a combination of. Let me go back to the chart here. Of the combination of the temperature and luminosity. So the further it is on this diagram, the shorter. So basically, it'd probably come down to the mass of the star. Yes.
You said that supernovas are like all of a sudden, but do we see the transition from like normal star to supergiant, or is that also a sudden thing?
So the question is, can we see the transition from normal star to a supergiant? I think I mentioned earlier that, for example, our sun is going to go through an expansion, then it's going to go through a contraction, then it's going to go through an expansion again. The period of that happening is, a long time. So from our point of view, I don't think we're going to be able to observe that change, but we can see instances of stars in different stages of that having occurred. Any other questions? Okay, well, that's it. Thank you all very much.